Okay, so you will be absolutely thrilled to know that we are moving away from normal curves and onto correlation. And correlation is something that I'm sure you've done several times before during GCSE, so you should have the basics of what correlation is. We're going to go through those basics today and then a few calculations that you can do to do with correlation, and then in the next few lessons we are going to do some serious calculations. We are going to calculate what's called Pearson's product moment correlations. So these are really, really in-depth, and if you thought standard deviation was tricky, this one is even more so. It's a lot of steps, but it's not hard, okay? You just need to keep up with the steps. But before that, we're going to go through the basics. So first of all, I just want you to pause the video here and think, what is correlation? What does it tell us? What is the point of correlation? So correlation tells us the relationship between two quantitative variables. Now remember, we use these words at the beginning, quantitative and qualitative. Qualitative tells us the qualities, it's things like colours. So it doesn't tell us numbers. Quantitative gives us values, and for correlation we must have numerical values. We need to have quantitative data. For the most part, it tends to be continuous quantitative data rather than discrete. Continuous, remember, are things like heights or weights, something where you could get a value of any number. Discrete is more like shoe sizes, where you're going to get certain numbers, okay? And it tells us how the dependent variable, that's the one that we measure and the one that normally goes up the side here, tells us how that one is linked or changes with relation to the independent variable, which we put along the bottom. So we might see that the dependent variable increases or decreases as we increase the independent variable. So we can have a positive correlation. This is represented by an upwards line of best fit, and you can see that all the data points are going up. Now what this means is, as you increase the independent variable, the dependent variable increases with it. So things where you might get a positive correlation could be things like height and weight. As you increase height, generally, not always, but generally, weight will also increase. Height and shoe size as well. So that's a positive correlation. A negative correlation is the exact opposite. It's a downwards line of best fit. And it means that as the independent variable increases, the dependent variable decreases. So as your measurement along the bottom goes up, the measurement along the side here goes down. So that's negative correlation. And then you can get ones where you just have absolutely no correlation whatsoever. You can't put a line of best fit on because the values are scattered all over the place. There's no pattern. So as I change my independent variable, the dependent variable could be any value at all, and I couldn't predict what it would be. There's just no link between them. Okay, we can also have strong, moderate, or weak correlations. So if you find that you do have a correlation, you might want to represent it as strong. And strong is where the points are very, very nearly on the line. If all of the points fall in an exact line, you can actually call it a perfect correlation. You must remember to say as well whether it's positive or negative. So here we have a strong negative correlation. Here we have a moderate negative correlation. We can still see that as we increase the independent variable, the dependent variable here is going down. But the points aren't really that close to the line. We'd probably put a line through the middle here, and the points aren't exactly on it, or even close to exactly on it. They're really quite scattered about. And then we get a weak negative correlation where the points are even more spread out. You can still see that there is that pattern, but the points are really quite spread out by this point. We can also have a linear or non-linear correlation. So if you have a positive or a negative correlation, it will be linear. It means that the points fall in a line. Okay, so that goes for strong, moderate and weak correlations. They are all linear. If you have no correlation like this, then it is neither linear nor non-linear. It is just no correlation. If your points fall in a pattern, look at this, this is still in a pattern, there's something clearly going on between the two variables for the points to fall like this. But it's not in a line, so we couldn't describe it as positive or negative because they're all over the place, but they're still in a pattern. These here are non-linear correlations. We can't describe them as positive or negative because as we increase the independent variable, the dependent variable is doing all sorts of wonderful things, but there's some kind of link between them. So that's non-linear, okay? So have a go at this. I'd like you to have a go at page 220 to 221, exercise 5D. So pause the video now and just have a quick go at those. Okay, so I'm just going to pop up the answers here, and you may have noticed that the answers for question 2 were there all along, so that was a nice treat, but check that yours fit with these. So pause the video again and just mark your work. Make sure that you're happy with all of these terms, and make sure you're happy with plotting a scatter graph. Okay, we have to be very, very careful when we talk about correlation. A lot of the time when people think of correlation, they think of two things that are linked together, and we assume that one causes the other. So for instance, with height and weight, we assume that as height increases, it causes weight to increase. That's not always the case with a correlation. Things can be correlated very, very closely, but they're not actually causations. They're not linked at all. So here's an interesting example here. Per capita cheese consumption. So that is the amount of cheese that is consumed per person in an area, correlates almost exactly with the number of people who died by becoming tangled in their bedsheets. Obviously, these two things aren't actually linked in any way. You are not more likely to become tangled in your bedsheets just because you eat a lot of cheese. If I was to plot them on a graph together with the number of the amount of cheese eaten and the amount of people dying by being tangled in their bed sheets, I would find a very, very close correlation. However, they are not caused by each other. So it's not a causation. If you want to see some more of these very interesting correlations, this is a website up here which gives you some weird things that are correlated together. Okay. So we're going to use the data from 2A now. So the data that you use to draw your first scatter plot. And I've just popped the table in here so you can see it. And we're going to talk about how we calculate, draw lines of best fit on a scatter plot, because it's no longer acceptable to purely do it by eye. So the first thing we have to do is calculate the mean of our first variable here, in this case x. If I calculate the mean of that, it gives me 31.25. I then have to calculate the mean of y, my second variable here, and write it in there as well, so that's 32.5. I then have my graph here, and what I do is I put a dot where 31.25 and 32.5 meet. Here I've got 31.25-ish and 32.5. I've just popped a little black dot where they meet. Then you can see that my line of best fit is going through that point. And that's the important thing. The line of best fit must go through the means of both of your variables. You should aim for that line of best fit to be touching as many points as possible. And you also want to try and get a similar number of points on either side of the graph as you can. So here I've got 4 on this side and I've got 5 on this side. So fairly similar. Okay? So once your line is going through the mean, you then need to spin your ruler around a little bit and find the best position for that line of best fit, going through as many points as possible and with a similar number of points on either side. You can then use your line to make estimates for any values that you don't already have. So here I've got a question: what would the value of y be for a value of x equals 30? So along the bottom I'd find x equals 30 here, and I draw a line up until it reaches my line of best fit. I'd then draw a line across from my line of best fit and see where it hits the y-axis. So that gives me 30. So for a value of x equals 30, my y value is also 30. So I can make predictions and estimates. Obviously they are not going to be exact. You can see here we had someone who had an x value of 30 who was actually much higher on the y value than 30. Okay, so your turn again. The questions on page 222 to 223, exercise 5E, please.